Hello, my dear warriors. Welcome aboard, welcome aboard, welcome aboard. So, today's session is basically an all-rounder session for all the students who want to ace in work, power, energy chapter. So, this is Shreyas here, your physics master teacher, and Vedantu, who has been teaching for a very long time. And what I aim to do in this particular session, because many students want to revise, understand in depth, and also apply the formulas and the concepts of work, power, energy. So this session is for all the students. And let me tell you the importance of this chapter, guys. At least one question, 100%, is going to come in NEET. Not just that, in many chapters like collisions or electromagnetic induction or even electrostatics or even rotation and SHM and so many other places, you will see the application of work, power, energy. So it will come like a combined concept. So that means easily you can crack 4 to 5 questions if you know this concept, and obviously you should know the other concepts as well. So take this like a very important high weightage chapter and put in your 100% effort. Okay. Hello Navya, Sandhya, welcome Anish, hello Yashu, hello Sumita, hello Devan. Nice to see you guys. I hope you guys are doing great, and I hope you guys had your dinner, and I hope you have hit the subscribe button, and I hope you have smashed the like button. If you have not done that, please do that right now, because it means a lot to me and shows your support, attendance and dedication. If you want such more videos, you need to do that. So let's begin with the class. Now, in work, power, energy, what are the main things that are very important? First thing is work, and how to calculate it, and how to understand which sign it is in, and how to to make the calculations when forces are variable and through graphs and all that. The next thing is power, how to calculate power and how to relate power, force, etc. The next thing is understanding the different forms of energy, like kinetic, potential energy. And the last one is applying all these concepts together in a principle called work energy theorem, or just mechanical energy conservation theorem. Okay, so let's understand all these concepts one by one. I hope you got the flow of the chapter. So these are the main 4 key areas which you are going to focus in this particular session. Yes. So Joel, definitely if you start from now, you can still crack NEET. And please don't spam, just like others are saying also. Hello Dev Prasanna, hello Sanitya, nice to see you guys. Bachalo. Good evening Sushma, good evening Yashu. Nice to see you guys. So what is work in simple words? Imagine that we have some object. Okay, so this is some body or some object, and on that object, let's say for example, there is a force which is acting. Okay, let's say there is a force which is acting, which is probably one of the many forces. It could be just one force, it doesn't matter. The body might move in that direction, might move in some other direction. Possible, no? You might be pushing something here, but if it is already moving there, then it will slowly turn in the direction of your push. So push and your actual motion can be in 2 different directions. Possible. So a lot of people generally have that confusion, why displacement in some other weird direction and why force in some direction. Doesn't matter. So this is your displacement of the body. This is the force acting on the body. Let's say the angle between them is theta. So what am I talking about over here? What is work? Work is basically the transfer of energy from one body to the other by an agent called force. So work, simply put, is nothing but what? The transfer of energy, via an agent. What is that agent, guys? The agent is called force that produces some displacement. Think about it. If I lift this remote, I am applying some force. Without that agent, it won't work. And I'm transferring some energy. I just had my dinner, just like you guys, hopefully, and I'm lifting this up. That means, I'm using my energy and I'm transferring it here, and I need force for it. I cannot just look at it and I'll be like, okay, listen, lift up, man, come on. I do like om, broom, broom, ram, kroom, and then it starts lifting up. No, it won't. It needs force. So that is that agent, without which work is not possible. The way I define work in physics is basically F cos theta into S, but in vector notation, you just call it as F vector dot displacement vector. This is the main formula for work, guys. Work is Fs cos theta or F dot S. What is this dot? This dot is your scalar product. I hope you remember this. I hope you remember this from vector lesson, but even if you don't, it's okay. This dot is basically telling there are two vectors on both sides, one vector here and one vector here. So when I put a dot here, it means take the magnitude of this vector, take the magnitude of this vector and multiply it with the cosine of the angle between these two vectors. That's it. So this is also called as dot product. This is also called as a dot product. It is also called as a scalar product. It is also called as a scalar product. The reason why it is called as a scalar product is very obvious. Work is actually a scalar quantity. Work is actually a scalar quantity. It is not going to have any direction. Do you anytime say, I am doing 100 joules of work in the north direction? Meaningless, right? Hello Chandan, hello Maha, hello Reena, hello Mukesh, hello Tanushree, nice to see you guys over here. Good evening Madhumita, hello Rakesh, hello Joyce Life. So you never talk about, sir, you know, I ate 80 joules of energy, sir, today while going in the upward direction. I just care about the number. Don't tell me which direction. I don't care. Yes. So whenever it is a cross, it is a vector. Very good, Rakesh. Dot is a scalar. Dot is a scalar. Cross is vector. Cross is vector. Okay. Cross will have sign in it. Dot will have cos. Dot cos. Cos dot. Cross. When do you do like this, guys? When do you do like this? Thank you, Anish. When do you do this? When do you do this? Oh my Lord, please protect me. I have committed a sin. I have committed a sin. This is a cross, right? This is a cross, right? Cross, sin, sine theta. Understood, guys? Vector. Understood, prayer? Got it? Now you will never forget it, no? Now you will never forget it. Very good. Awesomeness, guys. Now talking about the unit. Talking about the unit of work. What is the unit of work? So if I do 1 Newton, if I apply 1 Newton of force and 1 meter of displacement, then the amount of work done is basically 1 joule. 1 joule, correct? Similarly, if I convert it into dyne, so then it will be 1 dyne of force and I displace it by 1 centimeter, then the amount of work done will be 1 erg. And also remember, 1 joule is basically 10 to the power 7 ergs. This is the conversion factor, joules to ergs. Ergs is CGS unit and joule is obviously SI unit, something which you should be very well aware of. Now guess what? This is not the only way you can write. This is not the only way you can write work, but there is another way. Like, sir, what is that other way? Observe carefully. I can write cos theta with force or cos theta with S. It doesn't matter. I can combine both of these together or these two together. It will be interpreted in the different way. It will be interpreted in the different way, but the final outcome is the same. What do I mean by that? Observe. Just imagine if I tell you, come on boys and girls, this object, okay, is being pulled. It is having a force. It is also having some displacement. How about I split the force into two components? There is one force which is pretty much useless. I'm not going to bother about it so much, which is the F sine theta component. But the other component is F cos theta component, and that is basically in the direction of the displacement. So how about looking at it like this? It's a force in the direction of the displacement, multiplied by the displacement. Perfect, makes sense. So how about writing work is basically force in the direction of that displacement, multiplied by the displacement itself, right? It is also the right way of saying it. Also, I know another way of looking at the same thing. I'm just interpreting it in a different way. Instead of combining cos theta with F, how about S cos theta and leaving this force alone? Observe what happens. Now I will just show the force as it is. I'll just show the force as it is, but this time I will split the displacement into two components. Displacement into two components. One component will be here. This will be S cos theta. The other component is pretty much useless, which is sin theta component. Now, how are you going to write work, guys? How are you going to write work, guys? It is force into displacement in the direction of the force. So it is basically the value of that force. It is the value of the force multiplied by the displacement in the direction of the particular force. Both the definitions exactly reflect the same equation. There is no difference. It's just a way of understanding or way of solving the question for finding force. Is that clear? No, Kalandini, this is not collisions. This is only for work power energy. Bharani, I will be taking up 12th standard topics also very soon. Since board exam is far away, there is still time. Don't worry. I'll be doing it. Okay, great. I hope this is clear. Everybody understanding this point? Awesome. Sandhya, there will be a problem solving. Venkateshwaran, there will be a problem solving session. This with circular motion, because if you just take work power energy, it will be too less. I'll be doing circular motion and work power energy together. Then you will have a lot of fun. A lot of good problems come together. Now, guess what? Work also has a sign, guys. Yes, Deva Prasanna, it is a one-shot good lecture, big lecture. It is going to be very, very useful for concepts, formulas, understanding, application. Problem solving PYQ session separate with circular motion. Okay, so concentrate now. The signs of work. Okay, the signs of work. Just focus on whatever I am saying, guys. You don't even have to think. You don't even have to worry about, sir, what are you going to do next week? Don't worry. I know everything what you need. I know what to do, what not to do. Okay, even if you just blindly attend, you will be like, it is happening, it is happening. I don't have to break my head. Oh, I have to do that. Oh, I have to do this. Oh, when is sir going to? Don't break your head on that. Just follow me. That's it. You will see, you will be at a different league, in different level. Signs of work. Work has three signs: positive, negative, and zero. Positive sign. When I say positive sign, that means either the force and your displacement are in the same direction, or just it means that your force and displacement basically make an acute angle. Acute angle. That is the meaning of positive work. What it also means is that you're giving energy. Imagine I'm pushing somebody and that person is also moving in the same direction. Just imagine I'm pushing Pandu, just visualize Pandu, and I'm pushing Pandu in the same direction. I am doing positive work. It's a plus thing, plus marks, positive marks. I'm doing good thing. So positive. Understood, guys? Okay. Yes, Venkatesh, I'll be taking it up soon, not now. Okay. Next, there is a lot of time. Don't worry about it. Just focus on whatever I'm doing right now. Next thing is negative work. When I say negative work, that means the force is either opposite to the displacement or it is making an angle more than 90 degrees. That means as simple as it is making obtuse angle. Obtuse angle. Imagine somebody is going this way, but you're stopping him. He's coming like this. You're like, stop. Okay, I'm going out of the screen, but I hope you get the idea. The person is coming like this. I'm like, stop. So force is that way, displacement is here. So that is basically sucking away the energy from the system. That is a bad thing because I'm asking him to stop, retard. So it's negative work. Understood? Okay. Last thing is zero work, obviously. So zero work. How is zero work possible? You will be like, sir, it's obvious. One is, force is only not there. Oh yes, definitely. I don't apply only any force. The body is moving on its own. Okay. Maybe, something was just sliding. I have not done only anything. It's like, okay, it's just moving with a constant speed. Okay. No work. You have not done any work. You cannot take credit for that because you have not done anything. No force, no work. Okay. Second thing, you applied force. Your teacher gives you punishment. Imagine teacher gives you punishment and teacher is like, listen, push the wall. Only if you push the wall, then I will excuse you and you can sit on the bench. You start pushing the wall. Whole day you are pushing the wall. The wall doesn't move. Oh, what useless thing. Displacement is 0, work is 0. But you will be like, sir, I am tired, sir. So where did that energy go? It just went into your muscular energy. You have not done work on the wall. Did you transfer energy to the wall? No, right? Your energy is lost to the surroundings. You started sweating, increased metabolism, your muscular energy, it's lost within you, not gone to the wall. So work done on the wall is 0 because displacement is 0. Is that clear, everyone? And the last thing, how many of you can tell me this? How many of you can tell me this? There is one more way work can be 0. Look at the formula, probably you'll get an idea. Same timings, Bharani, usually at 9 o'clock or 5 o'clock or 7 o'clock. I'll be updating you the timings on the Telegram channel or on the community, okay? Yes, you can see cos 90 is 0. Cos 90 is 0. Ah, okay. So basically, what I mean to say is that the force is perpendicular to the displacement. Perpendicular to the displacement. How is that possible? Oh, imagine I move something round and round. I move something round and round. What will happen, guys? The displacement is along the circle. Displacement is along the circle. Force is towards the center, centripetal force. Don't you see displacement force is always perpendicular? You have not done any work. Like the moon going around the earth. Is gravity going to do work? No. Gravity is only changing the direction. It is not giving energy to the moon. Or you take a ball, connect it to a string and rotate it. Okay, rotate it and leave it. The string is only changing the direction of the ball. It's only turning it. It's not adding or taking energy. So no work done. So whenever forces are perpendicular, 0 work is done. Is that clear, bacha? Everyone with me on this? I hope this is understood. Great. So now that you know what is work and how to calculate work, let's do some basic questions on that. Okay? Let's understand some very, very easy and simple questions, and then we'll go to some more good, better questions. Just imagine, guys, there is this surface. Okay, we are just going to solve some examples now. This is an example. Okay, observe this. Imagine that there is a block over here, and this block has some mass. Let's say I call it m. Okay, or maybe I can give it some value, maybe 5 kg, maybe 5 kg. All right, and what happens is there is a force acting on it like this, and the force makes an angle, let's say 60 degrees here. Okay, the force is, let's say, 20 Newton. 20 Newton. And in this process, what happens is this block ends up moving, let's say, 10 meters. 10 meters is the displacement of the block. That is what it is. The question is find work by all forces acting on it. What is the work done by all the forces acting on it? Let's try to do it. Okay? Simple question. Let's start with simple, and you will see all kinds of questions, and there will be a separate PYQ session also. Okay. Now show all the forces first of all. Without doubt, how can you proceed? The first force that I'm going to show, is the weight. The weight is going to act like this, and that is 5g. There is also a normal force which is going to act like this. Correct? Normal force is acting up, the weight is going to act down. Okay. This force is acting at an angle 60 degree. I can split it into two components. One component is here, other component is here. Which component will you really bother? F cos 60 or F sin 60? Let's see if you guys can really think about this. Yes, work done by centripetal force is 0 Selvi. Yes, because it is perpendicular to the displacement. Every time perpendicular to the displacement, hence it is 0. Sin 60 says Dakshini. Madhumita also saying sin. Sandhya also saying sin. Sushma saying cos. Anish saying sin. Aishwarya saying cos. Firdos saying sin. Interesting, guys. See, which is the displacement? This. What did I tell you? If you remember correctly, force in the direction of displacement into displacement. This is the concept. Now you have to apply it. That's what I told you, right? I'm going to teach you applying concepts. If you remember formula F as cos theta, you will say cos. But no, this is not the angle with the displacement, it is the angle with something else. It's with the perpendicular. So actually speaking, it should be taken as 30 degree. So cos 30 is sin 60, or best way, the component is nothing but 20 sin 60. This is the component that you should bother. this is a completely useless component. It is just perpendicular to the displacement. You should not bother about that component. Is that clear? Everyone? Everyone? Yes, Tamil, I'll be coming there soon, don't worry. Now, over here, what we will do next is the work done by the external force will be nothing but force in the direction of displacement, which is 20 sine 60, multiplied by the displacement, which is 10. Acha. What is sine 60, guys? What is sine 60, guys? Come on, think and tell me. It is nothing but root 3 by 2. Root 3 by 2, correct? So now 20 into 10, 20 into 10, 200. 200 by 2, 100. So it will become 100 root 3. 100 root 3. You can also approximately say root 3 is 1.732. So this will be approximately 173.2 joules. So that is the work done by the external force. Similarly, if I ask you, what is the work done by gravity? What will your answer be? Gravitational force is 5g, displacement is 10. The angle between them, look at it carefully, displacement and force are at 90 degree. Force here, displacement there 90 degree. So cos 90 is 0. So the answer is 0. If I ask you what is the work done by normal force, what is the work done by normal force? Normal is up, displacement is 10, but again the angle is going to be 90 degrees, guys. Normal up, displacement there 90 degrees. So gone, it will be 0. Now, if I ask you what is the total work done? What is the total work done? Like it happens in your project. Like one person contributes a lot. These two people are not contributing only. Does it happen? Teacher has given you an assignment. Do this project, complete this homework together, solve this task together. One person very sincere does everything. Other two people are chilling. Chill madi. Relax. Enjoy. Lol. So this plus this plus this. Only this guy is doing work. Nobody is doing work. Nobody is doing work. So the final answer will be 173.2 joules. Everybody with me? Exactly. That's all. That's the answer. Cool, guys? Understood how to solve this problem? Very nice. Let's take up another question. Okay, let's take up another question. Now here you will also learn about dot product a little bit. So let me give a brief idea about dot product in case you have forgotten. So here is all about dot product. Here is all about dot product in case you have forgotten it. So imagine if I take unit vector I cap with unit vector I cap, what is the answer for that, guys? What is the answer for that, guys? I dot I, both are same vectors in the same direction. So 1 into cos 0 is 1, 1 into 1 into 1 is 1. So that is the same as j dot j, which is also the same as k dot k. Is that making sense? Everyone with me? Very good. If I do I dot j, then what will be the answer? I dot j, or maybe j dot k, or maybe k dot I. The answer for that will be 0. The answer for that will be 0. Very good. Now, with this, you get also another idea that, you know, what if I have a dot b? Is it the same as b dot a? I think so, because a dot b is ab cos theta, b dot a is ba cos theta, ab and b are the same thing. So yes, they are equal. So that is also equal to ab cos theta. Very nice. So then you might be wondering, sir, what if I have something I cap plus something j cap plus something k cap, okay, goes with dot product with something I cap, okay, something I cap, something I cap, something j cap, something k cap. What do you do in such cases? That something could be anything, right? 2, 3, 4, 1, minus 1, 10, anything. So maybe ax, ay, az, similarly bx, by, bz. What happens, guys, in such cases? I goes with I, because I dot j or I dot k is 0. J goes with j because j with I or j with k is 0. K will get multiplied with k because k with I or k with j is again 0. So guys, only multiply people of similar kind. Only multiply people of similar kind. It's like Audi guy, Audi lover will go with Audi lover, If somebody likes BMW, he'll be like, oh, you also like BMW? Okay, come on, let's hang out together. Oh, you like Bahubali movie? Even I like Bahubali movie. Come, let's hang out together. So people of similar kind hang out together in dot product. So what you will see is the answer is AX, BX plus AY, BY plus AZ, BZ. That is what the final answer is. Is that clear? Excellent, guys. Awesomeness. Hello Shagun Bhati, welcome bacha log. Hello Nikki, actually. Okay, now imagine I give you a question over here. Imagine I give you a question over here, something like this. If Pandu applies, how much force? I give it in I cap, J cap, K cap type notation. F is equal to maybe, I don't know, 10 I cap minus 20 J cap plus 4 K cap Newton, and displaces. What does it displace? A box from example 2 comma 0 comma minus 1 to 2 comma 4 comma 1. Okay, so this many meters to this many meters he has moved it. So what is the work done? So what is the work which is done by Pandu? Interesting question. This is very common again, if you notice. So let's see how to do this. See guys, in such a question, you are given the force, you don't know the displacement. So you need to find the displacement. How are you going to find the displacement? You know initial, you know final. It was here, it was there. Displacement, it was here, it was here. Now the displacement is just the change or the final minus initial position. Go by the logic. Displacement is always the change in position, change in the position value. That means it is the final position minus initial position. If you compare these two, you will quickly notice this is your final position and this was basically your initial position. Agree with me? Very nice. So let's write it down. Final position is basically 2I cap plus 4J cap plus K cap. Just the coordinates become the components. Minus, here you will see 2I cap, there is no J cap, oh there is only K cap, directly it is K cap guys. Okay, so minus, you can just say K cap, that's it. Now just subtract the 2. 2I minus 2I gone, zoop, vanish. Acha, so 4J cap is remaining, like I can see, K minus minus becomes plus, so 2K cap, this is nothing but meter, so that is your displacement. But I don't want that, I want the value of the work. Work is force dot product with displacement. So I need this. So 10 I cap minus 20 J cap plus 4 K cap dot product with 4J plus 2K. 4J plus 2K. So guys, like I told you, I goes with I. Oh, bichara, nobody is there for him. He likes Bahubali. Nobody is there who likes Bahubali. I will go with I only. Nobody is there. So gone. This will go with J. K will go with K. Acha. So what is the answer, guys? Check this out. Minus 20 into 4. Minus 20 into 4, guys, is minus 80, right? Minus 80, guys. Minus 20 into 4 is minus 80. Okay. 4 into 2. 4 into 2. 16, right? So plus 16 over here. Let's see how many of you have put up the answer. Very good, guys. Very good. Some of you have put up the answer over here. Oh, sorry. What did I just do? Why did I put 16? My bad. Sorry. 4 into 2. It's 8. My bad. Yeah. So this will just become minus 72 joules. Minus 72 joules. Everybody with me on this? Minus 72 joules. Very good. Hari Sudan. Who is Pandu? Pandu is our classmate here. Hari Sudan's question. Who is going to answer? Somebody has to answer Hari Sudan's question. He is confused. Sir, all this I understood, sir, but I didn't understand this only. First word only I didn't understand. Who is Pandu? Everything else I understood. Interesting. Okay, great. Yes, Harivasu, what is your doubt, bacha? Everybody clear till this point? So whenever displacement is not given, find that out and then find the work. So this is another beautiful, important type of question. Now, the next concept, and that is work by variable force. Work by variable force. Okay, work done by variable force. Now you'll be like, what is this work done by variable force, sir? Okay, let me explain this to you. Imagine there is a body over here. Now, at this moment, there is some force. Now, as it moves little bit ahead, let's say the force becomes small. Then as the body moves more ahead, then the force probably reverses. And then as soon as the body even slows down further, maybe the body slows down further, and then again suddenly the force becomes very large. The force is changing magnitude, direction, anything is possible, guys. So this is basically called as a variable force. So if you look at it graphically, it will make more sense. So imagine this is your displacement and this is your force graph. Okay, this is origin. You will see probably the force will suddenly increase, then it decreases, it changes the direction, and again goes positive. So anything can happen. Very good. Very nice answer. Very creative answer, Anish. Pandu is the assistant lecturer in Vedanta Physics department. Very true. Yes. Hari Hara Sudan. Oh. Okay. You're Hari Hara Sudan. So I have Hara also in between. Okay. So when I see it from here, especially when the screen is far, I miss out some words. Sorry, guys. I sometimes mispronounce your names. Happens with me all the time. Okay, so now what you do is basically you find small work. The small work done will be force multiplied by the small displacement. So dW is the force into the small displacement, but the total work is basically the sum of small work. Like for example, when you have to complete a project, one day only will not complete, no, the assignment, project, whatever task. One day you will do 5 pages. Next day maybe you took some printout of some picture and put it. Next day maybe you put some cover. Another day maybe you did something else. You had to decorate something. Another day you found one more article and you put it in the project. Next day you got some model, you put it. So every day you do small tasks. So the total thing is the sum of all the work that you have put. Same way over here, guys. When you do that in mathematics, it is called integration. What is it called? Integration. I have spoken about it many times in the previous lectures also. So you can just watch that basic maths class. So it is f integral dx. Okay, integral of f dx. So that is basically the way you should look at work done by variable forces. This is very important. This is variable force. Now, whenever there is integration, what should come in your head? See, when I talk about derivatives, what comes in your head in graphs? Yes, Prem Kumar, nothing happens overnight. If magnitude is asked, can we just take the modulus? Yes. But you take the modulus later on, not first. Do not take the modulus first and then multiply it, because then you are forgetting the cos theta value. Okay, Yashvardhan? Yeah, so when you think about derivatives, you think about slope. So when you think about integration, what do you think about? Area. Correct. So you have to find the area, but you need to be a little careful. When you are measuring this area will be positive area, because this is above the horizontal axis, whereas this area has to be considered as negative area, guys. This is basically negative area. Again, as it goes up, it becomes positive area. So the area also has sign depending on whether it is on the top or at the bottom. So when you find out the total work done, take the sum of all of them including the signs. Be careful. Okay, so you can also say that this is actually the area under the force versus displacement graph. The area under force versus displacement graph. Crazy. So we got to know about all of this. Let's proceed further to one more concept before going ahead. The next concept is the classification of forces into two categories. The two categories are, let's see. So forces can be categorized into two main categories. So what are the two categories? Observe this. The first category is just called as conservative forces. And the second category obviously will be called as non-conservative forces. non-conservative forces. Now, what do I mean by conservative and non-conservative forces? Let's try to understand them as well. Okay, just imagine if I have to push something from here to there, will the path which I take matter, or only where I start and where I end matter? What do you think? Can you suggest a course of IIT which is full of mysteries? Harihara Sudan, very nice question. Let me tell you, every branch is mysterious. It's just you need the eye for it. Okay, as simple as civil engineering also has many mysteries, right till computer science. Okay, so there is nothing like only this branch has mysteries. Everything, if you look deeply, has so many unanswered questions. Path matters, only initial and final position matter. I will tell you what, it depends. Some forces, only the path matters, how you go matters. Some forces, how you go does not matter. Where you start, where you end matters. Where you start, where you end matters. What is NEET exam preparation, guys? What do you think? Does the path taken to crack NEET matters? Or do you think, oh, I was here in 10th standard, I got this much percentage, and final destination, okay, I got a government medical college seat, or I got this college or that college. Does that matter? What do you think? Okay, it's an open-ended question. There is no answer for it from my side. I want you guys to think about it and probably put and debate about that in the comment section. It will be interesting to hear your views about it. Okay, so I'm not saying it is this or that. I just want to hear your views. That's it. So I just put a thought in your head. All right. Anyways, so in conservative forces, what happens is the path does not matter. Only initial and final position matters. So these kind of forces are basically path independent work. So only initial and final position matters, that's all. Whereas in non-conservative, the path matters for the work done. Path matters for the work which is done. Definitely. Not just this. If you start and come back to the same point, then the total work done is 0 in case of conservative. The total work for a closed path is 0. So if you start and come back to the same point, you will see that the net work done is big fat 0. Here work done in a closed path is not 0. If you come back to the same point, you will see it is not 0. I'll give you an example. Imagine you push something, push, and bring it back. You'll be like, every time I was pushing it. Force, displacement. Every time I was doing positive work. So how can the work be 0? Yeah, it is not 0. But there are some forces where you move it, sometimes the force will do positive work, sometimes it will do negative work, and by the time it comes back, total work done will be 0. So there are forces like that. So that will be conservative. Okay. Now what are the examples? Then you will be like, yes sir, this was conservative. Oh, why I didn't think about it. Best example is the gravitational force, or even electromagnetic force, or you can even say spring force, or even elastic force. All these forces are conservative in nature. Gravity, when you take a block up, will do, let's say, negative work. When you bring it down, it will do positive work. When you take it up, negative, positive. Total work done, 0. Negative plus positive, 0. But friction is not like that. You move it here, friction acts opposite, negative work. You move it back, friction acts opposite, again negative work. Total work done, negative plus negative, negative only. So work done in closed path is not 0. Exactly. So not just friction, guys. There are many people which are evil, like friction. Who are the evil forces? Friction, viscous force. If you have studied fluid mechanics or have some idea about viscosity, like honey, tar is viscous. Oil or water is not viscous. It's free flowing. Or drag force, air resistance force. Very bad, evil force. It will suck away the energy. It is non-conservative force. All these forces, including even normal force or even tension force, all these forces are non-conservative in nature. Everyone with me? Rakesh, buoyancy is a conservative force. Buoyancy, if you have to put buoyancy will be a conservative force. Okay, keep this in mind. Everyone? Yes, Rubesh, I have been in Tamil Nadu many times, bacha. Okay. Sir, does friction always do negative work? No, Prem Kumar, it can do positive work also. Okay, it can definitely do. If everybody is clear till these 2 points, work done by variable force and conservative, non-conservative force, let's go do some questions on this. Okay, here is a question on this. So let's see if you guys can figure this out. If a force in one dimension motion is given by F is equal to 2x cube Newton to move an object from x equals to 0 to x equals to 2 meters. Find the work done by it. Find the work done by it. Okay, start doing it, guys, and post the answers as soon as you complete the question and find the answer. Okay, I'll be explaining it slowly because some people might want to listen into the solution properly. That's okay. Okay, how work in a closed path non-zero? Sandhya? Okay, I'll just come to it. Hold on, just give me a second. Let me just complete this. Okay, one example of positive friction, definitely, Prem Kumar. Just hold on, let me just complete this question first. Observe now. Okay, I've heard all your doubts. I'll just do it. Hold on. So first of all, work done, okay, just imagine, is nothing but integration of f dx. Why am I using this? Because force is variable. So the moment it is variable, I have to think about, antenna will be alert. Oh, integration, tung karke. Okay, I have to do integration of 2x cube dx. But remember, there will be limits. It will be definite integration. You remember definite integration with limits? So whenever you see from here to there, from this to that, from now to then you will see integration with limits. The first point will be lower limit, then last point will be the upper limit. 2 is a constant, so put it outside. So integration of 2x cube dx, limits are 0 and 2 meters. Now this will become 2. X cube's integration is x raised to 4 by 4. 3 plus 1 by 3 plus 1 is 4, guys. Okay, and the upper limit is 2, lower limit is 0. Now the next thing that you're going to do is 2. First substitute 2, so it will become 2 raised to 4 by 4. Then substitute 0, so 0 raised to 4 by 4, and then subtract the 2. Guys, 2 raised to 4 is 16, right? Is nothing but 16. So this will just become 16 by 4 minus 0. 16 by 4, 4 2s are nothing but 8 joules. So that is basically your work done. Is that clear? Very nice, Shama. Very nice, Navya. Very good. Yes, no, joules. Very good. Yes, Dakshini. Yes, Chandana. Very good. Awesome, Selvi. Very good, Anish. Okay. Now going back to, I think 2 people had asked some questions. Yes, I'll be doing the entire chapter in this session itself. Okay. So the second point of non-conservative force and how can friction do positive work. Okay, work done in closed path is not 0. Just imagine, let's say I take this example. Imagine I take this body and I move it like this. Okay, I move it like this. This is the path along which I move it. Okay, fine. It's a closed path. What do you mean by closed path? You start and end at the same point. It need not be circular. It could be anything, but you should come back to the same point. That is the meaning of closed path. Okay. Now in this path, how will friction act? How will friction act? Friction will act opposite, right? Like this, like this, like this, like this, like this, like this. Okay. Every time it is acting opposite to the displacement. Here it will do negative work, negative work, negative work, negative, 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 negative. Whole time it was negative. Saddest fellow. Whole time it was negative. What is the total work done by friction? Positive, negative or zero? Negative. Is it zero? No, that's it. So work done in a closed path is not zero for forces like friction. Everyone fine? Clearo? Understood? But for gravity like forces, it will not be. So if you take this mass on the top and you go like this and you go like this and you come back over here, you will see as you go up, go sideways, go down and come back over here, you will notice that in this path gravity is acting down. Gravity is acting down, so it will do negative work. It is going like this, it is perpendicular, so it will do zero work. It is going down, gravitational force is also down, so it will do positive work. It is going like this, because it is perpendicular, it will again do zero work. Negative, zero, positive, zero, minus, plus, zero. So the total work done will be zero. Is that clear? Is that clear? Everyone with me on this? Very nice. The same thing you can also say about tension, bacha log. Imagine there is a dog. I have a dog, I take it to morning walk. Okay, morning, I take the dog to walk. So imagine this is my dog. Okay, so this is my dog. Okay, so I am taking it to the walk, for a walk, sorry. This is tension. Okay, this is tension. I take the dog like this. This is my path now. This is my path. I take the dog like this and it completes one complete lap or one complete round in my building, in my society, whatever. So guys, tension is like this, 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 tension is like this. Is tension doing positive work? Everywhere? Positive, 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 positive. Be positive. Come on guys. Total work done, not zero, na? So it is a non-conservative force. Is that clear? Is that clear? Everyone with me on this? Understood? Give me a thumbs up, guys. Okay, last thing. How can friction do positive work? Many people ask. Okay, just imagine. Just imagine. Imagine. I'm holding a block. And I'm holding a block like this. Okay, I'm holding something. And I move it. Or this way or that way. Okay, I just move it. So, imagine whatever platform it is on, it is under motion. If it is under motion, won't this also move? This will also move, right? Like this. When I move my hand, the block also moves, which is kept on the top. Who is going to move it? Friction, right? Where will friction act? This way or that way? Think carefully and answer. Think carefully and answer, guys. Think carefully and answer. The friction will act this way. Because who else will provide the displacement? Because the other forces are weight and normal. There is no other force apart from weight and normal, right? So who is giving that acceleration? Who is giving that motion? There is only one force, and that is friction. So in block on block problems, you will see the upper block, if the lower block is pulled, you will see the upper block experiences a friction in the same direction of the acceleration. Great. Great. So hence the answer for that is that the work done in the case of friction, work done by the friction will be positive. So a lot of people think friction can only do negative work. That is wrong. That is wrong. Okay, Harihara Sudan, we are not discussing pulleys and tension right now because that was a separate chapter. That is Newton's laws. I am going to focus more on work per energy. Okay. Kala Nidhi M. Let me tell you, bacha, even if I get one path, where work done is not zero, it is considered as non-conservative. It cannot be like, hey, come on, man, all these paths I did zero work. Only 3 paths I did negative work. Hey, come on, man, make me 70% positive, 30% you make me non-conservative. Either this or that. Even if you get one path where non-zero work is done, the tension is considered as a non-conservative force. Is that okay? Bicycle riding and running is positive friction. Well, that will come under separate category, rotational motion. Okay, in rotational motion, you will see friction will not do work in case of rolling motion of bicycle wheels. So friction actually does not do work in rolling motion. Okay, cool. So let's move on. Now, Guys, you are asking all random questions now. What is pseudo force? That is a completely separate topic. So guys, make sure that you are asking something which is relevant to the topic. If you ask me something, sir, what is pseudo force? Guys, I'm not here for that. If you are going to ask me relevant questions, fine, I'll answer, else that will be completely ignored. Okay, so stick to the topic. I don't like you guys deviating from the topic. Okay, now moving on to the next one. Moving on to the next question. Let's see if you guys can solve this. Imagine I take some body from here to here, and then from here to here, okay, and then here to here, imagine, or yeah, I'll take one more point maybe. Here to here, then here to here, and then here to here, and then here to here. Let's call this point A, B, C, and D. And let's say it's given to me that when I go from A to B, the work done is, let's say, 20 joules. 20 joules. When I go from C to B, the work done is, let's say, 10 joules. When I go from C to D, let's say the work done is, let's say, 40 joules. The question is, when I go from D, or rather A to D, when I go from A to D, then how much amount of work is done? Assuming it is a conservative force. Assume that it is a conservative force doing work. So how much work will be done to go from A to D? That's the question. Okay, let's see if you guys can solve this. Okay, think about it carefully. Okay, so guys, observe carefully. Since it is a conservative force, I know the total work done should be zero. So going from A to B, how much energy am I taking? I go from here to here, I take 20 joules. I take 20. If I have to go from B to C, oh, that is not given, but what I have been given is if I go from C to B, I will take 10 joules of energy. That means if I go from B to C, how much energy will I need, guys? If I go from B to C, obviously minus 10. If I go here, it is 10. If I go there, opposite, it's minus 10. Exactly negative of that. C to D is already given. How much is this? 40. The only thing remaining is this work. From here to here, here to here, here to here, and here to here. So I think I know what to do now. So total work done is 0. So work done from A to B is 20. Then plus negative 10 plus 40 plus work done from D to A is 0. Great. 20 minus 10 is nothing but 10. 10 plus 40 is nothing but 50. So 50 plus work done from D to A is 0. Correct, guys? Everybody with me? Excellent. So work done from D to A is negative 50 joules. But the question says A to D, not D to A. We have to find what is the actual work done from what is the actual work done from A to D. So work done from A to D will be negative of this. So it will be plus 50 joules. That is the final answer. Plus 50. I know, Sandhya, I know it is from A to D. So I found it from D to A. I know in the end I have to put a minus sign. So that is there at the back of the mind. Is that clear? Everyone with me on this? Okay, so this is how you can solve questions on conservative, non-conservative force, variable force. I've done some questions. Okay, let's do the next part. Okay, slowly we are moving ahead in this chapter, and I'm pretty sure you're slowly building that confidence. You're slowly remembering those things which you have probably forgotten, or probably you might have seeing these things for the first time, which is still good if you are able to grasp even 50 to 60% of it. I hope, guys, you are smashing the like button. If you have not done that yet, not fair. Okay, so let's go to the next part, and that is basically the types of energies. The first one being the kinetic energy. We'll talk about kinetic energy. Okay, so kinetic energy, guys, what is kinetic energy? It is the energy of motion. So energy which is basically due to motional. It is also called as the motional energy, not emotional. It is motional. It is not because of emotions, happiness, sadness, and all that. This is a scalar quantity. It is also measured in joules or ergs if it is CGS. Okay, and also interesting thing is it depends on your speed also. Just imagine you're traveling in a train or a bus. There is a luggage, there is a suitcase or something kept beside you. Imagine something like this. There is some bag kept beside you. You're looking at the bag. You are in the train or the bus. What is the energy of this bag, guys? What is the energy of the bag? No, Prem, we do not use sign for kinetic energy. We do not have plus and minus signs. Yes, Rubesh, obviously I will be sending the PDF, that's standard. Conservative is independent of the path. Yes, exactly. I think I mentioned that, Prem, in the previous slides. Is there any kinetic energy of this bag? I am sitting and observing it. Nothing. It's moving along with me. Wherever I go, I go here, I go here, I go here, I go there. What is the kinetic energy of the bag for me? Nothing. But for you guys, is this bag moving? Is this bag moving for you? Does the bag have some kinetic energy? Come on, guys, answer quickly, or else I'll keep moving, I'll faint. Come on, answer quickly. Does the bag have kinetic energy for you? Yes, right? Perfect. But for me, no, for me it is at rest. I'll be like, the bag has no kinetic energy. So what does it mean? What does this mean? Thank God, my hand is paining. Okay. So, guys, it means it depends on the observer. Depends on who is observing it. Depends on the observer or frame of reference. Observer's perspective matters. Your point of view matters. So it is a observer dependent entity. Okay. So what is the formula for kinetic energy, one might ask? The formula for kinetic energy is half mv square, and you can see speed square is there. So no sign. Kinetic energy is always positive. If somebody says kinetic energy is negative 100 joules, slap him on the face, throw him away. It's not possible, guys. So kinetic energy can at max, it can be 0, but it can't be lower than 0. So kinetic energy is always more than or equal to 0. Keep this in mind. Also, one more interesting thing, you can just multiply and divide by m. You can multiply and divide by m, so it will become m square by m into v square, which I know is also half mv whole square by m. Mass into velocity, guys, what is it? It's momentum, so it will also become p square by 2m. So that is also kinetic energy, something which you should remember. So half mv square or momentum square by 2m, one and the same thing. One and the same thing. Exactly. Yes, relatively. Yes, Anish, it depends on the relative frame or relative observer. Definitely. Crazy. Awesome. Let's move ahead to the next part. This was kinetic energy. The next energy that I should be talking about after kinetic energy, which is the energy of the motion, is nothing but potential energy. So let's talk about potential energy. When I use the word potential, what does it actually mean? It means ability. It means ability. Ability to do what, you might ask? Potential energy means what? Ability to perform work, and it is stored in that body. It is stored in that system or that body. Example, I take this remote, or I take some dumb object. I take some dumb object like this water bottle. You'll be like, sir, does this have energy, sir? Then I'll be like, okay, you want to know whether it has energy? You know what you should do? Leave it. Just leave it free. I don't want to do it. It will break. I will get nice beatings at home. Okay, so if I leave it, I know it falls. I know it will fall. It has ability to perform work. It has ability to manifest and show its energy. It will fall. It will get kinetic energy. Where did it get kinetic energy from? It got it from the potential energy because of gravity. If there was no gravity around me, it would be like, it is floating in space, just like it happens with astronauts in the International Space Station. So right now there is gravity, so it falls. Oops, I just held it. Okay, great. So same way, if I ask you, guys, do you have potential energy for cracking NEET? Reply to that with a fire emoji, or maybe put some ice. If you have potential energy, put fire. If you don't have potential energy for NEET, put ice. Yes, no? You have no? You have no potential energy? How do you know you have potential energy, guys? How do you know you have potential energy? Become free. Think freely, become independent. The more you are constrained, you cannot show your potential energy. This dumb water bottle also has potential energy, but it will not show it until I leave it. Fell down. Same way, you can also show your potential energy unless and until, only when rather, you free yourself. And when you start thinking freely, out of the box, creatively. Until you hold yourself, you will not be able to show your potential energy. Agree or disagree? Very good. Now this energy is also a scalar quantity. It is also a scalar quantity. It is also measured in joules, but there is a catch here. It is not, you don't talk about observer here. Here you talk with respect to something always. This bottle has gravitational potential energy. Okay, how much? So one person will be like 10 joules, other will be like 20 joules, other will be like 40 joules. Then you will be like, what? Is it 10, 20, 40? Then comes the answer. See, gravitational potential energy, spring potential energy, elastic potential energy, electrical potential energy, all these forms of energies are always measured with respect to something. Like, who is that something, sir? Something depends on you. It's always chosen. It's a line, or it's a system, or it's a configuration. It's a particular state which is chosen to be zero, and with respect to that you measure the energy. With respect to that, always. And thank you for putting up and lighting up the chat box, guys. Yes, we needed this winter fire. Very good. Thank you for warming up. So always choose some situation, some position, some line, some situation, some configuration as zero. Maybe when the bottle is here, I call it zero. Oh, right now you have zero energy. Okay, I tell him, listen, you have zero energy. Now, when I take the bottle here, oh, from this to here, oh, you have 10 joules of energy. So it's always measured with respect to something. You always measure it with respect to something. Understand that. So always measured, it's always measured with respect to something called as zero reference. Zero reference. Very important keyword over here that you are learning. It's always measured with respect to zero reference. For example, when you take a spring, thank you Yashu so much, thank you Rubesh so much, thank you Anish so much, and thank you everyone. When you keep it naturally, relaxed, chill, then it has no potential energy. But only when you strain it, when you compress it, then it has potential energy. So a spring in the relaxed state, spring that is relaxed, it has no potential energy. Or if you take charges, positive charges, negative positive charges, they will attract or repel each other. Correct? Depending on positive, negative, positive. You ask this charge, go there. This charge, go there. Like it happens, no? In school also. Two people are talking, interacting. Ha ha, he, hoo, ha ha. Teacher will be like, listen, you go there, that corner. You go there, that corner. What is he doing? I don't even know. What is he looking at? Why is he laughing there? I can't see him only. That guy is also saying, what is he doing? What is my friend doing? I can't see him. So no interaction, no potential energy. No interaction, no potential energy. So guys, that is considered as a zero energy state. So charges separated very, very far away from each other. Also, you can take for gravitation, block kept on a ground, block kept on, some level, on some ground level, you can say. These are all examples. That is the meaning of reference. So everything is measured with respect to that. Everything is calculated according to that. That is the meaning of zero referring. I'm referring to that and then measuring it. I hope this is clear. Yes, Prem Kumar, that's how friends are made. When the teacher shifts the thing, no? So then what happens? You make new friends. That person who was quiet also starts making noise. After a few months or few weeks, everybody is making noise. Teacher is under tension. So that's what happens. Okay, great. So let's move ahead and talk about the next part. Now there are few kinds of potential energy that you should know about. Usually when you talk about potential energies, what are the names that you have heard? Just put it in the chat box. What kind of names have you heard, guys, about potential energy? I think you would have heard about gravitational potential energy. Gravitational potential energy, 100% you have heard. What else have you heard? Have you heard elastic potential energy? Elastic potential energy stored in a rubber band, a stretched bow. Very good. Spring, very nice. Many people are saying spring. Very good. Spring potential energy. Very nice. Have you also seen something else apart from this? Yes, electrostatic. Electrostatic. Electrostatic potential energy. Electrostatic potential energy. Very nice. Perfect. So all these are examples of potential energy. Now the moment you look at their names, you should think like CID. You should think like CID. I have seen this person somewhere. Like it happens, no? Police is finding out missing persons report. Have you seen this person? Then suddenly one person comes. Ayyo, I have seen this person somewhere. Where have I seen this? Or sometimes also it happens with you. Oh, I have seen this person somewhere. I don't know. Is it ringing a bell? Is it ringing a bell? Is it ringing a bell? Can you do gravitation after this lesson? Okay, I'll think about it, bacha. I'll consider it. Just put it up in the comments or else it will slip from my mind. Have you seen these names together somewhere before this? Very good. Selvi is our CID. Perfect. Raw agent, Selvi Murugan. Very good. Perfecto. So let me go back a little bit. Let me go back a little bit. Over here, gravity, electromagnetic, spring, elastic, buoyancy. So guys, all these names are what? Conservative, non-conservative. Have you ever heard viscous potential energy, frictional potential energy, tension potential energy, normal potential energy, drag potential energy? Have you ever heard such names, guys? Have you heard anybody saying that? Nobody would have said that, right? If somebody tomorrow comes and tells you, or you say normal potential energy, one tight slap, guys. Okay, one tight slap. Tension potential energy, one tight slap. Viscous potential energy, one tight slap. Drag potential energy, one tight slap. Frictional potential energy, one tight slap. These, okay, all these are valid. So guys, what you should realize is that conservative forces have potential energy, or potential energy is associated with conservative forces. It is associated with conservative forces. Like, sir, why, sir? Only conservative. What did friction do wrong? What did friction do wrong? Friction is evil. Friction is evil. It takes away. You move the object here, friction will be like, come on, tax, come on, give me this, give me that. You bring it back, friction will be like, again, take it. But conservative is not like that. You move it here and you bring it back. Total work done, 0. Whatever it gives, it takes. Whatever it takes, it gives. So, whatever it gives, it takes. Whatever it takes, it gives. That means it stores and restores, stores and restores. So, it does not keep anything for itself when you come back. So, that is why it has ability to perform work. It has some potential energy associated with it. It can store energy. It can store energy. Look at this word. It can be stored. That is why it is associated. Understood? Exactly, Sandhya. Very good. Yes, Prem. Yes, Nitya. Very nice. Then comes the next topic, which is obvious. What is the relation between between conservative force and potential energy in general? Is there some kind of relationship? The answer to that is yes. You'll be like, sir, what is the relationship? Here it is. The work done by the conservative force is always the negative change in the potential energy. This statement has hardly been understood by many students. And you might have read this or heard this statement, and you would have seen the next thing which will come probably before also. But many people don't understand what it means. Let me make you understand this by providing an example. Just imagine if you have, okay, just imagine if you have some body, okay, and you move it up, Okay, you just move it up. This is the displacement. This is the first case. The second case, the same body, you just move it down. This is your displacement. Okay. Now think and tell me, guys, in each case, as you take it up, right, the gravity is going to act downwards, right? The gravity is going to act downwards. Mg is going to act downwards. So tell me, what is the work done by gravity? What is the work done by gravity? Is it going to be positive or negative? Just answer that. Just answer that. Is it going to be positive or negative? Displacement up, force down. Opposite. Oh, work done negative. Okay, work done is negative. Perfect. Perfect. Very good. Did the potential energy increase or decrease? Just answer that then. Did the body's potential energy increase or did it decrease? Oh, I take it up. Potential energy is increasing. Oh, so the change in the potential energy is positive, right? Change in the potential energy is positive, right? Everybody got it? Perfect. Now go the reverse way. Go the reverse way. As you go down, gravitational force acts down. Gravitational force acts down. If I ask you what is the work done by gravity, what is the work done by gravity? You'll be like, gravitational force down, displacement down. Angle is 0 because they are parallel. Oh, okay, it is going to be positive work. If I ask you change in the potential energy, it's coming from top to bottom. Top to bottom. It has lost potential energy. It has lost potential energy. So change in the potential energy negative. What does this tell you? If work done by gravity is positive, the change in the gravitational potential energy is negative. And if work done by vice versa, basically. If this is positive, this is negative. This is negative, this is positive. It's always opposite in sign. Now do you understand why this minus sign has come? Now do you understand why this minus sign has come? Everybody with me? Mind blown? Now you are like, oh, now I know why I should attend Shreyas Sir's class. Great. Awesome. Now what is work done formula, guys? Work done is small work, small change. You will be, sir, why did you write D, sir? Small change in potential energy, small work. More work, more change. Small work, small change. Obviously what you do, what you get. If you do small work, you will get small change. If you apply more work, more change, that's all. So work done is force into displacement, right? The conservative force into the displacement is negative U. Oh, bring this dx below. Bring this dx below. So guys, this will be minus du by dx. Minus du by dx. Very important formula. You know what this means? Force, the conservative force is the negative gradient of potential energy. Very important line that I'm writing here. It will save your day, even not just here, but even in electrostatics, magnetism, so many places, even in gravity. Awesome. Okay. Now you'll be like, sir, what the hell is this gradient, sir? Have you heard this? But what is this gradient? Gradient means change with respect to distance. Change with respect to distance. If it is dv by dt, du by dt, it is rate of change. Rate with time. If it is change with respect to distance, it is called gradient. So these are mathematical terms which you should know. The next time anybody says Pandu gradient, what will you think? Rate of change of Pandu with the distance. How is Pandu changing when he moves from here to there? If I just say rate of change of Pandu, then you're like, how is Pandu changing with time? Understood? So rate of change is purely time, but change with distance is called gradient. Got it? Awesome. Awesome, guys. Now there is a very interesting thing associated with this. So that is basically force versus, oh sorry, not force versus, what is this? U versus X graphs that you get. U versus X graph, potential energy versus displacement graphs. Imagine this is basically X, this is basically energy, okay? And I tell you, listen, the potential energy is changing like this, goes like this and goes like this. Every point there is different value of potential energy. What do I mean by that? I extend the spring so much, this is the potential energy, so much more potential energy, so much more energy. I take this mass here, this much energy, take it here, this much energy. So with position the energy is changing. Agree? Okay. So maybe there is some body, the energy increases, decreases, increases, decreases, something is happening, some random graph is there. of potential energy versus distance. Okay, now according to our formula, my dear students, F is equal to minus du by dx, minus du by dx. Now if you look at it carefully, if I draw a tangent over here, any place, if I draw a tangent, the slope of the tangent will be du by dx. So strictly speaking, this is negative slope of u versus x graph. Everybody agrees with this? U versus x graph slope is exactly what this is. Excellent. Now imagine if I ask you, at this particular location, is the slope positive or negative? Is the slope positive or negative? Put it up in the chat box. Fadafat guys, everybody should answer. Here is the slope positive or negative. If you have attended my basic maths class, slope, positive, negative, what is slope, derivative, everything you know. And if you have missed those classes, please watch it. Sir, which book is the best for question solving? MTG is there, our Tattva material is there. Best book is Tattva. Else if you don't have, no problem, use MTG or use DC Pandey, HC Verma, all these are good books. Okay, so positive, very good. So what will be negative of a positive? Minus. Here in this part, what you will see is the slope is positive but the force will be negative. Okay, everyone, but in this part or in this part, slope is negative. Negative of a negative is positive. So here slope is negative but the force will be positive. Clear? Understood? So that is why that negative sign is very, very, very important. Keep this in mind. Cool guys? Can we go ahead to the next concept? So we have learned what is potential energy, what are the different forms of energy, how is it related to conservative force using this formula, and how the graphs also have to be interpreted. Now the two main things which you should know is the formula for gravitational potential energy. What is the formula for that? So my dear students, if you have some body of mass m and you move it up by a height of h, then you are increasing the potential energy. So the change in the gravitational potential energy is mgh. U is generally the symbol for potential energy, just like you have K for kinetic energy. So I'm increasing it by mgh. But the same thing, if I bring it down, right, like this, then the change will be negative mgh. Always the change in the energy is what matters for most of the cases. Okay, great. So that is for gravitational potential energy. Similarly, there is a formula which you should know for spring potential energy or elastic potential energy. So imagine that you have a spring which is right now relaxed. It is at its natural length. So it does not have potential energy. This is right now natural length. It has no extension or compression whatsoever. Now the same spring, what you do, you either elongate it or basically you compress it like this. So you have stretched it by x or you have compressed it by x. In either of the cases, you have added a spring potential energy to the system of the value half k x square. This is the formula. So you should know this formula also. And obviously this is very easy. You have seen this probably in 9th standard itself. Spring potential energy half k x square. Everyone, what is x? Extension or compression? What is k? Spring constant. Remember, F is equal to kx. I hope you remember this. So when you pull, the magnitude of the force is kx. Is the minus sign important? Yes or no? Dhaswin, tell me, bacha, which channel am I teaching? NEET channel, no? NEET English channel. I am not wasting time, no. I am teaching for NEET only, bacha. with my classes. People last year, they used to watch my lectures on JE channel and then they cleared NEET. So if I'm exclusively doing NEET syllabus for NEET students dedicatedly, okay, for you guys, obviously you are going to like create wonders in NEET exam, definitely. Okay, yeah, so no need of minus sign. Why? Because it's magnitude. Minus, you can understand, yeah, whether it is this body or that body. It depends which body you are talking about. Accordingly, you put minus sign. So don't bother about minus or minus. Arey, waste it is. Okay, so don't bother about that minus sign. Great. I think we should solve some questions now. All right. So we have talked about this graphs, and we have talked about potential and as well as kinetic energy. So let's do some questions, guys. Let's do some questions. Okay, now look at this. If the force acting produces a potential energy of U is equal to minus 5x cube plus 4x plus 5 joules, example, then find the force at x is equal to 2 meters. That is the question. The energy changes with x. Find the force acting on it at 2 meters. Crazy question. What is the theory behind this question? From energy, how to find force? That to potential and force. Oh, potential energy and force are related. How are they related? Force is the negative gradient of potential energy. Force is the negative gradient. Gradient means rate of change with respect to distance. Okay. So now what is my next step? F is equal to minus d by dx. U is given. How much is it? Minus 5x cube plus 4x plus 5. Crazy. So minus minus becomes plus. 5 comes outside. It is just derivative of x cube. Just using simple rules of derivative, addition, subtraction. Minus plus becomes minus. 4 goes outside. Derivative of just x, guys. 5 is a constant anyways, but still I'll write it. Derivative of 5 with respect to x. Okay. So this will become 5. X cube's derivative is going to be 3x square minus 4. Dx by dx is 1. Constant's derivative is 0. So this will become 15x square minus 4. That is your force. But the question is at 2 meters. The question says at 2 meters. So therefore, force at 2 meters will be, put 2 over here. 15 into 2 square minus 4. 2 square is 4. 4 into 15 is 60. So 60 minus 4. Very good. So guys, what will be the answer over here? It will be nothing but 56 Newton. So this will be the value of the force. 56 Newton, not minus 56. Minus 56 will be there in the option to confuse you, because many people are going to forget the minus sign. All the people who forget the minus sign will get negative marks. If you remember, oh, there was a minus sign, you take into account all of the calculations, don't do mistakes, you will get the answer as plus 56 Newton. Okay, everyone, I'll try bacha acing. This week I'm planning to complete work power energy and then probably also go to circular motion. Circular motion also very important, and then I will take a combined session of PYQs problem solving on both these chapters. Okay, great. Let's do another question. All right, look at this. Imagine if the let's say I take a question on one of these things. I have taken all these things, right? Okay, let's take a question on the spring. Okay, if the spring is extended, by, let's say for example 2 meters, okay, if the spring is extended by 2 meters, a force of, let's say 40 Newton needs to be applied. 40 Newton needs to be applied, example. Now the question says, how much more work needs to be done needs to be done to further extend it by 2 meters, to further extend it by 2 meters. That's the question. That's the question. Let's see how many of you can do this. Okay, let's analyze the question first. Initially, the spring will be obviously at its natural length. There is no extension at all. There is some spring constant, but I do not know that. Then what happens is the spring gets extended by 2 meters. So the spring gets extended by basically how many meters? 2 meters. Then what happens? The spring is further extended by 2 meters. Further extended by 2 meters. That means what is the total extension, guys? What is the total extension? 4 meters, right? The total extension will be 4 meters, right? Very good. In the first case, how much force was applied? How much force was applied onto it? It was basically 40 Newton. Second time I don't know, but okay, I'll just keep it as it is. So for the first extension, using the force value is K times of X. So 40 is equal to K multiplied by extension. So the value of K will be 20 Newton per meter. That is the initial extension which is giving me the spring constant. Why do I need spring constant? Because I think from this I can find how much energy this has. Then I will try to find how much energy this guy has. This has this much energy, this has this much energy. Oh, why did the energy difference come? I'll think, I have done work. Because I did work, that's why the energy changed. So that's the reverse thinking that I thought. So guys, if I ask you, what is the initial energy? You'll be like, it is half K initial extension square. K value is 20. What is the extension? Extension is 2. So 2 square. So correct, guys? So 2 square is 4. 4 by 2, 2. 2 into 20, right? This is 20, is nothing but 40 joules, of course. This is 40 joules. Everyone with me? Very good, Saran. Awesome, awesome. Now, last part. What is the final energy over here? What is the final energy over here? Half K X final square. K value 20. Okay, put 20. X value 4. Oh, there. Acha. 4 square, 16. So this will become 20 and 2 cancels becomes 10. And this is 16. So this will become 160 joules. This is your final energy. So the last part will be, what is the work done? The work done will go in changing the potential energy. That means final minus initial. That means 160 minus 40, which is nothing but 120 joules. So the work done is 120 joules. Not minus, plus. I will do work because I am increasing its energy. I have to perform positive work. Only then it will increase its energy, not negative work. Is that okay? Always change is final minus initial, not initial minus final. Change final minus initial. Okay, everyone? Clearo? Understood? Very good. Prem, Maha, Sakti, Reena, very good. Jairam, very good. Awesome, Dakshini, very good. Crazy. Proud of all of you. Okay. Let's do another question. Imagine if the momentum of a body increases by, let's say, 100%, then kinetic energy increases by how much percent? That's the question. Let's try to figure this out. Okay, I think it is directly formula based. Maybe I just need to be careful about the calculations of percentages and all of that. Momentum and kinetic energy, how are they related? Kinetic energy is the momentum square by 2m. That's the formula. Okay, fine. Now, according to the question, the kinetic energy, the momentum increases by 100%. So the final momentum will be initial momentum plus that increase which has happened. How much is 100% of P? If I tell 100% of Shreyas Sir means complete. If I say 50% of Shreyas Sir means half the body, 25% hardly anything. 75%, 100%, 50%, 75%, 100%, 90%, 80%. Guys, obviously it means P only. So final momentum has become 2P. Okay, final momentum has become 2P. So my dear students, what will be the final kinetic energy? It will be 2 times of P whole square by 2m. Okay, 2 square is 4, and what I'm left with now is P square by 2m. Now observe carefully, this P square by 2m is exactly the old kinetic energy. So it is 4 times the old kinetic energy. So this is your final kinetic energy, guys. This is as good as saying it is K plus 3K. So what does this mean? This is the increase. This is the increase, right? So the final kinetic energy is original plus 3K. So how much is that increase? It is basically 3 times or 300%. That is the answer. Exactly 3 times, or in percentage terms, 300% of that. Excellent. That's all you have to think. That's how these questions come usually in NEET exam. Moving on to the next part. And this is the last few things, okay, that we are going to see. And that is power now. Let's go to power. Powerful. How fast you can do work. So power is all about how fast work is done. Work is done. It is also rate of doing work, rate of supply, or basically doing, or basically losing energy or work. Energy or basically work. That is what power is. So strictly speaking, the formula for power is dW by dt. Now work done, why dW? Rate of doing work. Rate means always with the respect to time. Now dW by dt, I can also write it as force dot displacement with respect to time, because work is force into displacement. This is small work, so small displacement. This dot, because that's how it is. Force, I can separate these terms and write it beautifully as ds by dt. Now what is ds by dt? What is ds by dt? It is nothing but velocity, rate of change of position, displacement. It's velocity. So power is also force dot product with velocity. As simple as that. Either use this formula or use this formula. It's one and the same thing. If you talk about power, it is also a scalar quantity, because you can see dot product means scalar product. Answer is scalar. Answer is scalar. Jaram, I take classes here regularly. Thank you so much. Okay, then also another thing is the unit. 1 joule of work, if I do it in 1 second, it is called 1 watt of power. And there is another unit which is called horsepower. 1 horsepower is roughly speaking 746 watts. 746 watts, something which you should know. Very simple. Okay, everyone with me? All right. Also remember one more thing. Power can also have signs like this. Power can be positive, definitely. In the case of force which is parallel to the velocity. So force is basically parallel to the velocity or making an acute angle. Then you will see power is basically positive. There is another case where the power can be also negative. That means you are sucking away the energy. So either the force is opposite to the velocity, or the force makes an angle which is obtuse with the velocity, just like work, guys. And there is another case where the power can be a big fat zero, then you will see the force will be perpendicular to the velocity, or there is no force only. One and the same thing. Yes, there are many memes on what? And I was seeing one funny conversation between 2 British people. One guy's name is Not, or surname is Not, last name is Not. Another guy's name is What. He's like, hi, my name is What. He's like, okay, what is your name? He's like, yeah, my name is What. Then he's like, no, what is your name, sir? My name is What. Then this guy's like, who are you? I'm Not. No, I'm not asking who are you not. Who are you? And he's like, no, my name is Not. What are you saying? I'm like, I am What. So a very funny conversation between 2 British people that I was just seeing today. Crazy. HP full form. Hindustan Petroleum, no. Horsepower. Horsepower. Okay. So one average horse has a power of 746 joules per second power. Okay. Great. So let's probably see a question on this. If a block mass m falls from rest, what will the power be after time t? That's the question. How will the power be after time t? Let's try to solve this question, guys. So first visualize. There is a mass m at time 0. It starts falling from rest, so no velocity at all. After some time it comes down over here. The same mass, it has gathered some speed, so there is some velocity. This is at some time. Okay, so the question is, what is the power by the gravity? What will the gravitational power, in fact I should put, what will the gravitational power be after time t? Gravitational power means I need gravitational force, so let's show the force. Force is in this direction, crazy. So the force will be basically weight, which is mg. Okay, so the power due to gravity will be force, gravitational force multiplied by the velocity of the particle. Gravitational force is mg. The problem is with this guy, velocity. How much is this velocity, guys? How do you find it out? I think we should use kinematics because it is accelerating due to gravity. So I know final velocity will be initial velocity plus acceleration multiplied by the time. Final velocity is v, initial velocity is 0, rest, acceleration due to gravity g, time t. So v is basically gt, so just put it over here. Just put gt over here. So what are you going to get? The power due to gravity after time t is m, g into g is g square into t. That is the answer. Done. No, I didn't want height because height was not given. Only in terms of t I can find it out. Okay, so Selvi, that won't be the answer. Clearo? Understood? Amazing. Great. I'll definitely come up with some timetable and some timelines for all of you guys in the days to come. It's a very important topic for you guys, I know. Let's come to the last few things, and that is basically, first is work kinetic energy theorem, and then we'll talk about mechanical energy conservation. Imagine I have a system. There are many bodies inside of it. Inside of it, there could be, internal forces as well between them. So these are basically internal forces which act within the system, and maybe from outside also they are experiencing something like external forces. What happens is, in such cases, because of these forces, these bodies might change direction, speed, etc. So their kinetic energy might change. And it is basically proven that when all these forces perform work, their total work changes the total kinetic energy of the system. As simple as that. So basically put, the total work done by all the internal and external forces changes the total kinetic energy of the system. As simple as that, nothing else. So I can just say that work done by internal forces plus work done by external forces is basically change in the kinetic energy. Change is delta, that's all. So I can also combine these two as the work done by literally everything, all the forces is final minus initial kinetic energy. This is the main statement of work kinetic energy theorem. All the forces, when they do work, they change the kinetic energy. That's all. Yes. Now, very interesting thing that you should know about work kinetic energy theorem is this. If imagine all the work done by all the forces, if it is positive, then what will happen, guys, to the kinetic energy? What will happen to the kinetic energy? That will also be positive. Change in the kinetic energy will be positive. If LHS is positive, RHS will also be positive. This means that the kinetic energy is increasing. What does it mean? Kinetic energy is increasing. Imagine some body which is being pushed like this and it is moving also like this. So obviously the speed will increase. This is the meaning of work done is positive. Same way I can say if the total work done is negative, change in the kinetic energy is negative. So the kinetic energy is basically decreasing. Example will be the body is moving here, but the force is over here. So in such a case, the speed is definitely going to go down. That is the meaning of it. Is that clear, everyone? Awesome. Now, this was work kinetic energy theorem for all of you. There is another theorem or another law which helps you solve the problem. You can use either this or that. I will tell you how to use both of them in the next slide. But for now, just observe this. First of all, what is mechanical energy? Mechanical energy. Mechanical energy is just simply put nothing but potential energy plus kinetic energy. The sum of potential energy and kinetic energy is called as mechanical energy. Simple. Now there is a law which talks about the law of conservation. How energy cannot be destroyed or created. Basically, law of conservation of mechanical energy. Law of conservation of mechanical energy. What does this law tell me? Conserve means it maintains. Conserve means it maintains. Law of conservation of marks. If you maintain your pace of studies, your marks neither go up nor goes down. If you do something extra, then it goes up. If you do something bad, then your marks go down. So, this law says that my total mechanical energy is a constant. When will my mechanical energy be constant? Simple. If evil guys, who are the evil guys? Non-conservative force. Example, friction, viscous, drag, all these, tension, normal. These people do not do anything. They might stay quietly, they might be there, but they should not do any kind of work. They should not give nor take. Then I will see the total energy will be conserved. Like, friction is not there, or friction is not doing any evil job. Air resistance is not there. So when I drop something, all the potential energy gets converted into kinetic energy. So these examples where you pull a bow and release the arrow, the potential energy gets converted into kinetic energy. So there is no loss. Then you will see that mechanical energy is conserved. So you will see kinetic plus potential is constant, and this is only true if the work done by non-conservative force is zero. Evil people. Who are the evil people? Friction, normal, tension, viscous, drag. These people should not interfere. Else, whatever work they do will change. Else what will happen? Whatever work the non-conservative force will do, that will go in changing the mechanical energy, basically delta I. So that will change the mechanical energy of the system. As simple as that. Let's take an example to understand this or even this theorem. Okay, this theorem as well as this law, I will make you understand using a simple question. Observe this simple question, guys. Just observe. Imagine there is a surface, there is a wall over here, okay, right now. And just imagine that there is a spring like thing over here, and there is this block. It's a smooth surface. This mass is coming with some speed, let's say v. After some time, what happens? This mass will hit the spring will get compressed, the mass will slow down, and stop. And then it will be thrown back. Slow down, stop, and thrown back. When it stops, that time the spring is compressed by maximum amount. So I'll show that over here. Observe, the spring is compressed by maximum amount. The block has compressed it maximum. So when max compression happens, what will be the speed? It will have come to rest for a moment. It has come to rest for a moment. The question is, how much is this maximum compression? How much did it get compressed by? Is that clear? Okay. So let's try to solve this question. The first method that I'm going to use, method 1, is work kinetic energy theorem. Let me use this theorem and find out the value of x. Okay. How do we do that? Okay, let's draw the free body diagram. Let's start by it. In this system, what are the different forces? Put it up in the chat box. Obviously, weight will be there, normal will be there, and spring force will be there. These are the forces, and the box's motion, the motion of the box is over here. So if I use this theorem, the total work done by all the forces is change in the kinetic energy. So it will be work done by normal plus work done by gravity plus work done by spring is final minus initial. Okay, think. How much work will normal do? Oh, it's perpendicular, guys. It will not do anything. So put 0. Gravity is again perpendicular. So nothing. 0. Spring force is here. Why is it here? Because when I go there, spring will push me this side. Force and displacement opposite, so minus. Always work done, spring, energy, etc. is always half kx square. Standard formula. Final energy, rest for a moment. So that means no kinetic energy. Minus initial, half mv square. So put half mv square. Minus half cancels. So it will become kx square is equal to mv square. That's it. But I want x exactly. So x square is mv square by k. So therefore x is equal to v under root m by k. So this is my final answer. Everyone with me? So I have ignored friction. Friction and all is ignored. So I have assumed that all the surfaces over here are basically smooth. So ignore the friction. Everyone? Cool? Okay. Now this was one way of doing the question. Believe me, there is another way. That method 2 is via conservation of energy. Conservation of energy principle. So let's see how to do this. Whenever you have to apply this theorem, I suggest personally, please make a story in your head. Look at the entire situation, simulate it in your head, think what is happening, and make a story of which energy got converted into which energy. Oh, my mom gave me this much money, I spent it here, I gave it to my friend gave some money, in the end of the day, I had this much money. So make a mental calculation like that. This block, it was moving. So what will it have? Kinetic energy. Okay. It went, stopped. Why did it stop? Spring. Oh, the spring stored the energy. Did anybody else suck or give the energy? No. Gravity? No, it did not go up or down. Nothing else. So can I not say that the kinetic energy of that block went into the potential energy of the spring? This is the story that I made in my head. See if this makes sense to you. Is that making sense to all of you? Everyone? So guys, what is the kinetic energy of the block? Is it not half mv square? What is the spring potential energy? Is it not half kx square? Half gone. So mv square is equal to kx square. So x square is equal to v square m by k. So therefore x is equal to v root m by k is it not the correct answer? Same thing, but which one is giving you the answer easily? Which one is giving you the answer easily? Happy Pongal to all the kids. Thank you so much for remembering. Belated rather. Which one is giving the answer easily? Which one is more easy to understand and apply? This, right? So usually you are going to use this, not this. And you're like, sir, why did you teach it? I'll tell you when I will use this. Because there will be some situations where this will not be so easy to make a story. Not everybody is a good story writer. Sometimes mechanical energy, potential energy is there, then kinetic energy is there, then friction is there, then suddenly this work is done, then that is done. You are like confused that this is doing work or this is taking work, whether this is energy is increasing, decreasing. You are confused. In such cases, avoid this, go through this, because this is simple. Because in those complicated cases where story making becomes difficult, because you just have to write, oh, this force, this force, this force, this work, this work, this work, positive, negative, this much, this much, this much, and solve it and get the answer. So this is very systematic, but lengthy, but it will give the answer. This one is short, but if you are able to make the stories. Got it? Everyone. Awesome. So guys, that's all that I wanted to teach you today. We have covered right from work to finding work done for variable forces and integration and area. Then we also went to conservative, non-conservative forces. We also talked about kinetic energy, potential energy, and there's some which is mechanical energy. Then we also spoke about how potential energy is related to conservative force and their relationship and their graphs. And we also talked about power and how it is the rate of doing work. Towards the end, I have shown you two methods, and you should be knowing both the methods, work energy theorem and energy conservation, and their conditions when it is applied. That all these things will be available to you in the PDF, where in the Telegram, where in the link is there in the description box. Go ahead, find it out, you will get it. And if you want more help, you know where to find the crash courses or even the long-term batches. It's all there in the chat box. Just find it out and you will be able to enroll happily. Okay? So you know what to do. After the lecture is over, put it up, mark your attendance, even if you're watching it recorded. Sir, I watched this lecture. I had a lot of fun. Just put up a small smiley or if you don't have anything to say. Makes my day. Okay, and I will do that one comment that you put, right? It will give me so much of energy for the next class. So make sure you hit the subscribe button so that you don't miss my next class, which is going to be on Thursday if I'm not wrong. And also make sure you smash the like button if you enjoyed the session, of course. And stay regular, keep working hard, use the notes and build up the confidence. Let's crack NEET together. Okay, that's it from my side. Have a good night. Hasta la vista, Captain Shreyas signing off.